So hello everyone, welcome to NPTEL course of Coherence and Quantum Entanglement. This is week 2 and today is 3rd February 2024. This is a course offered by NPTEL through SWAM portal, and this is the course instructor is Professor Anand Kumar Jha and myself Nilakshi Shanapati, your TA, and today is our second problem solving and doubt clearing session. So today, before going to some discussion, I would like to tell you few more details, like the which I tell every day at the beginning, that we have a Google Drive link through which you can get all of the things that I will share with you, as well as I will discuss here the slides and the class notes, and maybe much more question and answers which you require for your examination preparation and so on. So this is the Google Drive link, and there is also there is also some YouTube link. You can search by my name, or you can let me take some moment to open YouTube and share the link. Okay, so this is my YouTube channel where you can see that all these files are already uploaded. There are few playlists of those which I have taken the classes, like the Python for data science, nuclear astrophysics, and now it is going on the coherence and quantum entanglement course. So here you can go and get my from my YouTube channel. You can get the recorded videos of this lecture, of these discussion sessions, as well as maybe before the examination you can get some quick tutorial for examination purpose. So okay, so if somebody missed some class or some part of any class, then you can obviously visit this YouTube channel for further for revisiting these things, or like for first time, whenever for according to your convenience, whenever you want to see, you can watch that. Okay, and this is the drive link. So today my plan is to discuss about your Mach-Zhender interferometry setup, and somebody has some problem or question on the ask a question portal. There I found that this kind of question was there, why we are what is how to realize this setup in practical, like in laboratory, and what is this setup, and how to like each and every details of it, and as well as you asked for those questions like why we are talking about single photon level, highlight level, low light level, etc. So all of those discussions today we will carry forward. Okay, so now let me let me tell about this temporal basis and whatever like the let me formally introduce second order coherence theory on temporal basis. Because the picture whatever you are seeing here, that is nothing but a Mach-Zhender interferometry, through which we want to study time energy interference in time energy basis or the temporal basis. So here we look at the temporal coherence effects and ask the question as to how field vibrations at a given space point r0 at time t1 we look at the temporal coherence effects and ask the question as to how field vibrations at a given space point r0 at time t1 are correlated with field vibration at some point, same point, but at different time t2. So this is to answer this question. So to answer this question, we considered a Mach-Zhender interferometer as it is shown with this figure, that we will take the help of this to understand that. So the field at R0 is divided into two by a beam splitter, which is written as BS. I hope you can see this. Figure where which I am describing at this moment. That the field at position R0 is divided into two by a beam splitter, and the two fields reach the detector after having traveled for times t1 and t2. The electric field VRT at the position R, that is the output state after coming to the after meeting at the second beam splitter, that will now become, let me write here, VRT equal to K1 VR0 T minus T1 plus K2 VR0 T minus T2. So this is the electric field at position R, corresponding to the figure that I am showing. Here VR0 T minus T1 and VR0 T minus T2 are the electric field vibration at the source point R0 at time T minus T1 and T minus T2 respectively. Therefore, by studying the intensity at the detector, one can study how the field vibrations that are separated by time T1 minus T2 are correlated. But before starting the calculation, let me remind you once more that some essential mathematical concepts and physical situation must be in consideration, that they must follow the physical scenario such that we can do the further calculation. So revise is that I talked about stationarity. In stationarity, and as well as spectral representation of a time domain spectral representation. Let me write here. Spectral representation, then time average, and ergodicity. Okay, so all of these things I have described in the previous class. I just wanted to recapitulate it. That's why I just mentioned all of these once again. I have I have given you the some problem and related to and some related problems to this area we discussed, where we need to know about stationarity, ergodicity, time average, all those things. Okay, now we have this field. Sorry. And we are now prepared to answer the question as to how to quantify the correlation between the field vibration at T minus T1 and T minus T2 from the figure that we have, like Mach-Zhender Interferometer. Now the electric field VRT at the detector position, as I have mentioned, is like this. So here VR0 T minus T1 and T2 minus T2 are the electric field vibration at R0 at time T minus T1 and T minus T2 respectively. Therefore, the intensity at the detector is I am doing one by one calculation, just v star v, one by one step. No, I will not step jump. This bracket, angular bracket means the ensemble average, and plus the CC terms, which can again be written as K1 square IR0 T minus T1 plus K2 square IR0 T minus T2 plus K1 star K2 tau R0 T minus T1 R0 T minus T2 plus Cc. That means it's complex conjugate version. This IR0 T minus T1 is nothing but ITT, we can write it as IT minus T1 only, which is V star V star T minus T1 V star T minus T1. You can understand that this one, and this one is IR0 T minus 2, and this gamma, capital gamma, is of our interest, which we call as the cross correlation function. Okay, we can write this in terms of just gamma T minus T1 T minus T2, which is cross correlation function. These things all are told in your lecture. Just I am writing all this equation again and again, just because I will apply all of these formulas for solving the questions, as well as our purpose is to revise the lecture and understand the lecture as a whole. That's why I am repeating. So after doing this thing, I will solve one question, then again we will come to discuss something and again solve one question, and the discussion session will run like this. Okay, so now this gamma can be written in this manner. Which again can be written as e to the power I r gamma, as like complex variable representation. Because now it can be the phase function can be complex also, and the function as a whole can be complex also, as we are dealing with the electric field itself, not just only the intensity. Now we see that the intensity at the detector depends on argument of gamma, that is arc gamma. And if you do the further steps and write the I, then it will become K1 square IT minus T1. I am not writing R0 because it is just a function of time, that's why, plus K2 square I T minus T2 plus 2 K1 K2 I T minus T1 I T minus T2, gamma t minus t1 t minus t2 cos of arg gamma plus phi k, maybe some dynamic phase can add, that's why. So see, the intensity at the detector depends on argument of gamma and it changes in a sinusoidal manner as a function of argument of gamma. This sinusoidal dependence is multiplied by the degree of coherence, which is modulus of gamma, and the visibility of the interference pattern is defined like which is okay. We see the visibility is proportional to the degree of temporal coherence, where of course this gamma is degree of temporal coherence. And for the special case where k1 and these first two terms are same, then we have v equal to just gamma t minus t1 gamma t minus t2, this part only. That is, the fringe visibility equals to the degree of coherence. This is called degree of coherence. Now we know the cross correlation function is connected to the cross spectral density through the generalized weiner-khentchine theorem. Which is gamma t1 t2 minus infinity to plus infinity, as it is 2t, we are dealing with two parameters, so it is like this, and we can write it as w omega 1 omega 2 e to the power minus I omega 2 t2 minus omega 1 t1 d omega 1 d omega 2, and Fourier transform of it is w omega 1 omega 2 1 by 2 pi square minus infinity to infinity gamma t1 t2 e to the power I omega 2 t2 minus omega 1 t1 dt1 dt2, and this we call as, and this is the generalized weiner-khentchine theorem basically, which says the two time temporal functions tau t1 t2 and is a two-dimensional Fourier transform of the cross spectral density, that is w omega 1 omega 2. This is the cross spectral density and this is the two time temporal correlation function. Okay. Therefore, depending on the frequency correlation of the source, depending on the frequency correlations of the source, a source field can be divided into three types. One is no correlation. When no correlation, when the source has no correlation between its different frequency component, the cross spectral density function becomes W omega 1 omega 2 is equal to S omega 1 delta omega 1 minus omega 2. The degree of spectral coherence in this case become degree of spatial coherence means I just want to say that it is the gamma by this factor, this function is actually written as mu, represented with mu. Excuse me. Okay, so it becomes mu omega 1 omega 2 equal to delta omega 1 minus omega 2. That means there is no correlation. As we have seen before, having no frequency correlations implies that the source is stationary in time. That means stationary in times. This means that the cross correlation function depends only on the time difference and the intensity of the source is dependent of the origin of time, and that the ensemble averages can be replaced by time averages. And now we can write I t minus t1 equal to I. There was one maybe assignment question related to this type of theoretical approach. You can now solve by using this concept. Tau, where tau is the t2 minus t1. We find that for sources having no frequency correlations, the intensity remains constant, and the intensity remains constant over time, and the degree of temporal correlation depends only on the time difference. That is the tau. Such sources are also called continuous wave fields. Many common laser sources like helium neon laser pointers have CW, that is the continuous wave fields. Now case 2, when there is perfect correlation between different frequency components, then the cross spectral density now becomes equal to, we can directly take it out from the ensemble average. The temporal coherence function and the intensity of such source are thus given by this. And temporal correlation if you found, then it will become T1, T2. This was the cross spectral density, and this is the temporal correlation function, which will become V star T1, V T2 directly. So now we can write IT as gamma TT at same time becomes minus infinity to infinity V omega the power minus I omega t d omega square. Okay, so we find that in this case the temporal correlation function and the intensity both depend on the time arguments, and the intensity has a temporal structure, the exact form of which depends upon V bar omega. The degree of temporal coherence is also always equal to 1, that is gamma T1 T2 equal to 1. This type of correlations are found to be in the pulsed laser. Pulse structure in the intensity profile. Let me change the layout. Okay, so okay, this type of correlation found in fast laser. The pulse structure in the intensity profile is due to the fact that the frequency add up coherently. Now, another thing is partial correlation between different frequency. Most realistic sources are effectively partially correlated field in their frequencies. The types of sources discussed above are two extreme points. A source can be partially correlated in many different ways. However, the most commonly used model is the Gaussian cell model. And the mathematical represent of the cross-spectral density of this Gaussian shell model source is given by excuse me. I'm so I apologize for my health. Exponential minus omega 1 minus omega 0 square plus omega 2 minus omega 0 square by 2 omega square, and exponential minus omega 1 minus omega 2 square by 2 omega c square. So in this case, the temporal correlation function and the intensity both depend on time arguments, and the degree of spectral coherence in this case becomes just only this part, depends upon this part. Sorry. Thus we find that in the limit omega c tends to 0, the above source essentially becomes a continuous wave laser source, and in the limit of omega c tends to infinity, it becomes 1. Therefore the Gaussian cell model source and therefore if omega c tends to infinity, then it became 1, which tends to a perfect correlation source, and when omega c becomes 0 and it becomes infinity, then it becomes 0. That means only there is no correlation between two photon source, two field point source. Okay. Now this now after discussing all of this thing, I will just go to 1 minute. I'll go to some problem and then I'll discuss again about some other topics. So this is the problem to this is today's problem. Which is telling about one of the most often encountered random processing in optics is a Gaussian random process. The probability density associated with Gaussian random process looks like given as px 1 by root over 2 pi sigma a to the power minus x minus mu whole square by 2 sigma square. And then it is asking that verify that the above distribution is normalized. Then second, find the mean first moment and second moment of this distribution. Also calculate the standard deviation. Calculate the third and fourth moments. Do these moments yield any new information about the process? First, point A. Using the definition of V, we can write it as our 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 target is to find out one minute. So so it is saying that we have px 1 by root over 2 pi sigma e to the power minus x minus mu square by 2 sigma square. Now we need to check it for normalization. That means minus infinity to infinity px dx equal to 1 or not. Question is this, check. So for that excuse me, one by root over 2 pi sigma minus infinity to infinity e to the power minus x minus mu whole square by 2 sigma square dx, which will 1 by 2 pi sigma, and this part this is a special integral which you need to know how to solve it. If you solve it, then it will become 2 pi sigma, that means it will give you 1. Now how to solve this solve this Gaussian integral, that is your homework. Okay, if you cannot solve this integral, then we can do it, or otherwise maybe I can tell you that you need to transfer it to the polar coordinate, and to conserve its dimension you need to take the Jacobian and multiply the Jacobian in the function such that you get proper normalization factor or for proper integration. And then again after transferring to the polar coordinate, you need to substitute something to simplify the equations, and then it will reach at one known format like which you can integrate, then you can solve it. Basically first substitute x minus mu as equal to x dash, and then therefore and therefore it will become something like something like e to the power minus x dash square by 2 sigma square dx dash. Now again you can use some tricks to solve it, or either you can directly integrate this I, and whenever you will you need to use x equal to r cos theta, y equal to r sin theta, and transfer x to r dr d theta, and for that you need the Jacobian also. And I hope you all know about how to calculate Jacobian. All right, so this is the first question, and so this part I will find this integral. This is your homework. Okay, the second part, it is telling that find the mean and the second moment of this distribution, also calculate standard deviation. So B, part B is telling mean, that means x minus infinity to infinity x p x dx. substitute then if you calculate, you can consider x minus mu equal to x dash thus it becomes x dash plus mu e to the power minus x dash square 2 sigma square dx dash. Now first with this term and secondly it is with this term. So x dash e to the power minus x square, it becomes on 0 plus 1 by root over 2 pi sigma. It I just told it becomes 2 pi sigma. So mu into. So finally mean becomes mu. Second moment is x square, and that is x square px dx minus infinity to infinity. Right now just substitute excuse me. Now again do the same procedure, substitute x minus mu as x dash and calculate further. Then what you will get is then what you will get is 1 by root over 2 pi sigma integration minus infinity to infinity x dash square e to the power minus x dash square by 2 sigma square to sigma square, and now dx dash plus mu square root over 2 pi sigma plus 0. Okay, so now the second part and third part we already have. What you need to do is to solve this first part of this integration, and this is I can consider like let me just write this x dash square e to the power minus x dash square by 2 sigma square dx dash minus infinity to infinity is equal to is equal to minus infinity to infinity x dash square e to the power minus alpha x dash square dx dash, where alpha can be considered as 1 by sigma square. Then you can write now this integration as d by d alpha minus infinity to infinity e to the power minus alpha x dash square dx dash, and this becomes d by d alpha root over 2 pi into 1 by root over 2 alpha. This kind of equations, like whatever I have given you as this homework, that you need to know how to solve this kind of standard integration. You can also remember that what is the basic form of e to the power alpha x plus beta x square kind of beta x square kind of integrations, and this is just that kind of integration where you can using which you can actually calculate that how to solve this kind of problem in this course, because in this course these standard integrations are very important. Over 2 pi into 1 by 2 alpha. Now it becomes 1 by 2 alpha pi by alpha whole to the power half, that becomes sigma square 2 pi sigma square whole to the power half, that is equal to root over 2 pi sigma cube. So finally, if you substitute, then x square or second moment of x become 1 by root over of 2 pi sigma root over 2 pi sigma cube plus sigma mu square root over 2 pi, that is equal to sigma square plus mu square. Hence the standard deviation becomes root over of x square minus x square equal to sigma square plus mu square minus mu square equal to sigma. And now if equation 1, I mean if we consider this kind of repeating trick, then you can solve the part C also, which is telling calculate the third and fourth moments to and do this yields moment yield any new information about the process. So this question I am writing the answers. You guys please go step by step and find out what will be the answer, that if you are getting this answer or not. Okay. I am giving you some times, maybe 5 minutes, where you can try to solve this question, solve this part of finding out this calculating this third and fourth, and tell me if this is coming or not. Okay. I am giving you about, let us wait for 2 minutes that you try in meanwhile, and again we will come back for further discussion. Okay, so uh, after I hope all of you were able to solve this. Meanwhile, why I want to discuss is that the special case of a stationary quasi-monochromatic field with Gaussian spectrum can also be there. For the special case of a stationary field, that is no correlation between different frequency components, we have the case like this one. Let me go. This is a no correlation thing. This is a no correlation thing. Now, so we can write this equation now for this no correlation case as k1 square I plus k2 square I plus 2 k1 k2 I gamma of tau cos argument of gamma plus phi. In many situations, the field of interest has a spectrum that is quasi-monochromatic. This means that the spectral width delta omega of the source is very small compared to the central frequency omega 0 of the source. That means if you have this spectrum and this is the central frequency omega 0, then this delta omega is much smaller than omega 0, then it is called quasi monochromatic. From our discussion, we know that the autocorrelation function of a stationary random field is the Fourier transform of spectral density. That means gamma tau is equal to minus infinity to infinity is omega e to the power minus I omega tau d omega. Okay, and substituting omega 0 plus omega 2 for omega and assuming quasi-monochromatic, we can write the autocorrelation function like minus infinity to infinity is of omega 0 plus omega to the power minus I omega tau d omega. Okay, and now we are considering s omega as like 1 by root over 2 pi delta omega e to the power minus omega 0 square by 2 delta omega square. Here delta omega is the width of the spectral density function. And it is called frequency bandwidth or spectral bandwidth of the source. So for the above, I equal to gamma tau 0 is equal to 1. Now if we use the weiner-khentchine theorem and utilize this, then you will get we will find the temporal correlation function for this spectral density. Okay, and that will become gamma tau equal to e to the power minus I omega 0 tau e to the power minus tau squared by 2 tau c square, where tau c is equal to 1 by delta omega. And the complex degree of coherence function can be written like gamma tau is equal to small gamma tau is equal to capital gamma tau by gamma 0. Okay, so that will again become this only. Okay, so we obtain the following expression. That means if we have a very stabilized source, from this one we can tell, this is very important relation, you may get some question from here, that if we have very well stabilized laser, then frequency bandwidth of it has 1 megahertz and coherence time then becomes 10 to the power minus 6 second. That means coherence length becomes 300 meter. Diode laser of frequency, if we have diode laser of frequency bandwidth 1 gigahertz, then the coherence time becomes 10 to the power minus 9 second and coherence length is 0.3 meter. And sunlight 100 terahertz, which becomes coherence time tau c 10 to the power minus 14 second and coherence length 3 micrometer. Okay, so it is not like that sunlight do not have any coherence coherency in coherence length. Rather, every source of light has some coherence length. Maybe that is much more or much lesser, but you can find some coherence. Similarly, you can do the second order coherence theory in spatial terms also, and you can realize it much more nicer way, as we are practically aware about the Young's double slit kind of experiment and Young's double slit experiment. Okay. So now maybe we can again solve one problem from this part. From this temporal part. It is telling, let VRRT be a real field, and let's assume that it can be represented in terms of Fourier components as VRRT is equal to integration VR omega to the power minus I omega t d omega, which can be represented in terms of V star RT plus VRT, which I have already mentioned in the previous class also. Now VRT is called the complex analytic signal corresponding to the real variable VR of RT. In coherence theory, the time average intensity IR of the field at position R is defined as IR proportional to V star RT VRT. On the other hand, in classical electromagnetic theory, the intensity is given as IR or C epsilon 0 VRRT, the time average, then so that this equation and thus prove that two above mentioned definitions are related as IR of RT, IR of R 2C equal to 2C epsilon 0 IR. So we will solve this problem, but before that, let all of you guys give a thought regarding this, because you will get this kind of question in your examination. Meanwhile, I will stop I will mute myself and give you some time to solve this, and after you are done, I will maybe ask someone, and if not, maybe I will solve this problem in detail. Okay. So now let us solve this question. It is given as 1. So from the definition we can write one minute. Here you need to calculate first minus v r square r t dt, which is equal to minus infinity to infinity v r omega dash to the power minus I omega plus omega dash t d omega dash dt. Okay, just the Fourier transform in with the square in omega and t. This is what we can write. Now 2 pi integration minus infinity to infinity dt is already used. This is what it becomes. This is equal to 2 pi minus infinity to infinity v r minus omega d omega is equal to 2 pi minus infinity to infinity v r omega v star r omega d omega, which is equal to 2 pi minus infinity to infinity v r omega square d omega, which is equal to 2 into 2 pi 0 to pi v r omega whole square d omega. Next up we are using the definition of VRT, and we will show that v star rt dot VRT, now it will become equal to 2 pi integration 0 to infinity v r omega modulus square d omega. Okay, so let us calculate that now. Let me write in the next line. Excuse me. The minus I omega t d omega 0 to infinity v r omega dash the minus excuse me d omega dash dt. is equal to minus infinity to infinity, 0 to infinity, 0 to infinity, v star r omega v r omega dash e to the power minus e to the power plus I omega minus omega dash t d omega d omega dash dt. This can now be written as 2 pi 0 to infinity v star r omega v r omega delta omega minus omega dash d omega dash. That will become again 2 pi 0 to infinity v star r omega v r omega d omega. That will become 2 pi 0 to infinity v r omega square d omega. So we will also have that now minus infinity to infinity v r omega square d omega equal to minus infinity to 0 v r omega square d omega plus 0 to infinity v r omega square d omega. Now this will become minus infinity to 0 v star r omega v r omega d omega plus 0 to infinity v r omega square d omega. We can substitute omega equal to minus omega, and minus infinity to 0 becomes v r omega minus omega v star r minus omega d omega plus 0 to infinity v r omega square d omega, which will again become 0 to infinity v r omega v star r omega d omega plus 0 to infinity v r omega square d omega, which will become 0 to infinity v r omega square d omega. Thus from all of this we can now write 0 to infinity v r square r t dt equal to 2 minus infinity to infinity v star r t v r t dt equal to 2 pi minus infinity to infinity v r omega square d omega 2 into 2 pi 0 to infinity v r omega square d omega. I r becomes c epsilon 0 v r square r t 2c epsilon 0 v square r t t. Okay, so this is how we can solve this problem. So before going to the another problem, let us discuss the spatial temporal part now, spatial correlation part now. So in this section we will look at the spatial coherence effects at a particular frequency omega. Actually we will talk more in detail in about spatial domain in the next week. But before that, but let us discuss let us start discussing some few things in this regard today itself. So, in order to keep things simpler, special effects at a we will consider special effect at a particular frequency only. So, as we represent electric field V or T in terms of position and time, and we can do its Fourier integral and go into the Fourier basis. Similarly, similar things we can do in the RZ or rho Z basis, which is nothing but the spatial coordinate. And the field can in general be a random, and in such situation the Fourier transform is just symbolic and physical meaning will only be ascribed to correlation function. So uh, we now can ask the question that if I have a position rho 1 at z equal to 0, how rho 2 at z equal to 0 are correlated spatially with each other. And for that, to answer that, we need to describe and quantify the spatial coherence in terms of degree of spatial coherence, and it can be studied through the Young's double slit interferometer experiment. We all are aware about Young's double slit experiment from very childhood, but you will get a new perspective after this. Not new perspective, but the real perspective. Now, in a Young's double slit experiment, one collects the fields emanating from spatial location and the spatial location rho z on a screen. The field rho z is can be written in terms of like k1 u rho 1 plus k2 u rho 2, and due to the propagation, it can add some phase. And after all of this, we can write we can write the output field and whichever it is meeting at the screen. Again, here we will consider the stationarity, we will consider angular spectrum representation of a space domain field, just like the temporal domain. And of course, we will see how when it propagates, how the phase adds and how it changes. We just need to solve the Helmholtz equation for getting any propagating solution. That we will do. We will also talk about angular correlation function, which is just the Fourier transform of these, and then Fourier transform of this cross spectral density function. And then we will reach to the intensity function derivation, where we will get the degree of angular correlation function. And of course, by using the weiner-khentchine theorem, whatever we have done in case of temporal, you will do that in case of spatial. And of course, we will consider the space averaging and ergodicity also. We have we of course the things whatever we have understood as of now about no correlation, perfect correlation, partial correlation, all of those scenario will arise here also. And we will do the propagation of correlation, thus the Wolff equation solution, then the propagation of and Van Sitter-Jarnicke theorem by solving the Wolff equation. On all of those we'll discuss in very detail from in the next class. So today we can solve this problem. Maybe let me describe this problem whatever we have, and you can solve this in the meanwhile, or you can try it at home. Then maybe we'll ask you that if anybody of you have solved it. If solved it, then I will ask to explain it. If not, then we will solve it again. So it is saying that consider a field Vt given by a e to the power minus I omega at plus b e to the power minus I omega bt, where omega a and omega b are two frequencies and a and b are two real numbers. Find out the cross spectral density function W omega 1 omega 2 of the field, and find out the intensity of the field. Find out the cross correlation function gamma T1 T2 of the field. Is this field stationary, at least in the wide sense, and find out the degree of coherence of the coherence function of the field. All of these things I have described in very details. I have also calculated how to calculate this intensity, cross spectral density, cross correlation function, how to find stationarity, degree of coherence, everything in terms of some other field which is given like in the temporal domain only, which was given like this thing, which is given in this thing. Okay, and this thing mean, I hope you can see this thing. Okay, and now if the same thing you do in terms of this question whatever given here, then you need to just follow the same rules and same process whatever I have done today with some other field, then you will reach to answer. I will give you answer, provide you answer. Maybe you can give a try at this moment itself, or you can try at home also. Maybe I'll give you 2 minutes to try it by yourself, and then today I will end up the class, and we will discuss the further things on the next class. Let me give you 2 minutes for another 2 minutes. If you one have any question, or if you want to solve, let me give you 2 minutes if any one of you have any questions, or like just to think that how to solve this problem, etc. So 2 minutes for you again, and I am going through the pages whatever I have I have already solved, and you need to follow the same things for your this question. All right, so 2 minutes starts now. Just give a thought. I will come back again and end up today's class. So again I will share this YouTube channel link for YouTube channel link, where you can get all of these videos where it will be uploaded, and again the drive folder link which will be shared with you via SWAM from NPTEL via SWAM portal. And and okay, so today I don't have anything more to show to you, so maybe today we can end up this class sooner, and then we can discuss this, continue this discuss on next class. And as of now, whatever your assignments are there and your questions answer we have solved, all are related to your assignments, and you will be able to solve the assignments by following this. Thank you.